Yeah, about me, my name is Jonas Wenger, and this is I am a PhD student at KTH in Stockholm, Sweden, and this is joint work with my supervisors, Philip Haller and Paris Carbone. And what I'm presenting today is our ongoing work on what's called portals and extension of Dataflow Streaming for Stateful Serverless. And it's our work is really at the intersection of distributed systems and programming languages. So I guess you'll see that throughout the slides. Before I start, I want to talk about Dataflow Streaming, so we all have a common understanding of what I mean by this. So typical systems that you would consider Dataflow Streaming are Apache Flink, Google Dataflow, Kafka Streaming, and so on. And these are distributed, so you're running the computations on many computers over the network. And they also employ this exactly once processing guarantees. So you have some very strong guarantees on these systems, so you can actually have certain business logic running on them. At the bottom, I have a figure showing a stateful Dataflow pipeline. And it's a physical plan of a pipeline. So you might only have two tasks in the logical sense, but here the tasks are replicated and they're executing in parallel. And you need to send messages between them. And we have some distributed streams. The streams are where the events are transporting to the pipeline. And we see we have three black lines. By this, I'm trying to show we have three different channels because one channel might not be enough for a very large amount of events. Okay, so I hope this clarified some things. And I'll talk about the motivation of our work. So the core motivation is really that a lot of this critical infrastructure, the Google services, Uber, Netflix, and Spotify, and much more, they're all powered by distributed services, and distributed services are really very complex compositions of communicating services. Here I'm showing a very much simpler example, but I'll have this throughout the talk. We're looking at the shopping cart example. It consists of three services. We have a cart service and an order service and an inventory service. The client might, for example, send an add item to cart request to the cart. And for this, the cart needs to check with the inventory, that is, send a message to the inventory to see whether or not this item is in the inventory. And the inventory will have to respond back to the cart whether or not the item was in the inventory. So we have some communication pattern here between the services. And for these types of applications, we usually have three requirements here. One is the guarantees, and here I will typically talk about exactly what's processing guarantees, which if you haven't heard of it, it's more or less that you can assume that there are no failures in your system, that it should behave as if there are no failures. The second one is on performance, and for performance, you oftentimes you need to scale up to very, very large amounts of requests per second if you have a large e-commerce, for example. Still, you need to have very low latency, so this is very tricky, of course. And the last one is programming flexibility. So even you still need to be able to express the applications that you want to write, is what I mean by the last one. Okay. What should I say? Well, building distributed services is very difficult. I think that's no surprise. The main reason are failures. Computers might crash and messages might get lost. And so for the messaging thing, you might try to send more messages until you get a response back, but then you have to deduplicate messages also. So things get very messy very quickly. We had a talk on Tuesday by Asterios in the Rebels workshop. He also spoke about this at great lengths. The second thing is, again, we need to scale up a lot, still with good response time. And the system might execute in very heterogeneous environments. And last but not least, we're also managing very sensitive data. in these systems, user data. And so we have to still make sure that we do this in the proper way with respect to GDPR. So this is really asking too much of the regular programmer, and if I'm honest, it's too difficult for me also. So yes, but what can we do instead? Instead we have this like a new way of programming these things, which I will call stateful serverless. And in stateful serverless, we have systems like durable functions, Apache Flink State Fun, Cloudburst, Belly, and these are all really, really nice to use systems. What exactly is stateful serverless? Well, first of all, it's stateful. That is, the system manages state. This is what's different to AWS Lambda, where this state is not managed by the system. And the second difference is that, the second thing is that the serverless part the system should manage all of these difficult parts with failures, with reliability, with execution, and so on. And the key idea here is that the program should only need to write the business logic and shouldn't have to write the execution failure logic. Okay. So as I said, there are many great systems, but there are still a few things that can be improved according to us. First of all, we think that it would be nice to have a Dataflow Streaming style composition in these systems. The second thing is that it would be useful to have some event ordering guarantees in these systems. And the third part is also that the cycles are typically supported with restrictions, you can say. For example, cycles, or if you have two entities in durable functions, they cannot call, an entity in durable functions cannot call another entity, because call is a blocking operation and it's a cycle in some sense. So cycles are always a bit tricky in these systems. Of course, what I want to present now is portals where we're trying to improve these things. What is portals? It's built on Dataflow Streaming. We try to harness the good things of Dataflow Streaming, which is the exact amount processing guarantees and the great performance you get. However, we have to have some more extensions so that we can define multiple services, so we can have dynamic topology, and so we can actually have cycles and even RPCs, because these things are typically not something you find in a Dataflow Streaming system. Yeah, this is an overview of our concepts. And here we can see we have the services we had before, the cart service, the order service, and the inventory. These are workflows, we call them. And workflows are the stateful data flow pipelines. Then we have atomic streams, which are like the distributed streams that connect the workflows together. It's not in this figure, but you can have cycles between workflows across with atomic streams. However, within a workflow, you cannot have cycles. That's a restriction. And then we have these things called portals, which enable this RPC-style communication. And you're not expected to understand the model yet, so I'm going to show you some examples, which hopefully gives a bit of an intuition. The first example, I hope the numbers are big enough, by the way. The first example shows a generator. A generator can generate an atomic stream. We have two atoms here. The first atom, an atom is this big yellow circle. And the first atom contains the event 1, and the second atom contains a single event 2. And the workflow is very simple. It simply decrements the events here by 1. So the events are integers, and they're decremented by 1. And the output is, again, two atoms. The first atom has the event 0, and the second atom has the event 1. Are there any questions about this example? Okay. All right, so we can do cycles, of course. So here we have now a cycle you can see from the output of the workflow kind of back. And the way we can do this is by having a sequencer. The sequencer can take two atomic streams and combine them into a single totally ordered atomic stream. Again, here we generate now the event 4. And in the workflow, we will take this event and decrement it by 1. And then if the event is larger than 0, then it's allowed. Otherwise, it's filtered out. So the output, what will the output be? Well, we'll repeat this 4 times. The first time we have the output 3, a single event output 3. Second time 2, 1, and then it terminates. And so this kind of style is actually not supported in Dataflow streaming systems like Apache Flink. So it's actually surprising. Okay. Yes, the third example, now it gets a bit more interesting. Now we have 2 events in every atom. I hope it's still readable. I see some squinting eyes, unfortunately. But we have 3 atoms, 2 events in each. We also have files, so the input is always 2 files, and then we have a task which computes the aggregate sum of all the events and always emits the incremental sum. Okay, this is a rather common compute task also, and the output, if you cannot see it, it has 3 atoms with 2 events always, so, and the output is 5, 10, 15, 20, 25, 30. So that's what you can do with stateful computations also. Again, a very simple example. Now the question is, quite often you have a stateful workflow, a stateful pipeline, but you would like to inspect the state of it. The only thing you can really inspect in Dataflow, typically Dataflow streaming, is this output, the output of the stream. You don't have any means to really inspect the state. And this is where we would like to have a kind of an RPC call where we can either inspect the state or send a request and get some form of a response back from this task. So this is what the portals do. At the bottom, we can have another workflow here, which is triggered by these empty events. And the bottom workflow will now send a request to the top workflow to always ask what is the current aggregate sum. Okay, and the output we get in this case, we could get 10, 10, 30. To notice that the output is not necessarily deterministic. We have two separate threads working here. We have 2 workflows that are working separate. However, we only ever get numbers back that are divisible by 10. Okay. The reason is in these, if it's not legible, we have 10, 10, 30, and we only ever get a number back that is divisible by 10. That's because we only ever observe values that have been computed by a complete atom. So we only ever observe what happened here and here. We never observe something when half an atom has been processed. So this is quite a useful property. They only ever observe a kind of a complete computation. Any questions, perhaps? Yes.
Sorry, I might be missing something, but why is it not 10, 20?
Because these are, well, we don't have a order between the events that are, when this workflow will consume an event or consume an atom in processing, and when the top one will. So they do it in parallel, 2 different threads, and then the request is also a thread. So.
Oh yeah. Could you repeat for the question for the virtual audience as well?
Oh, sorry. Yes. So the question was why we don't observe 10, 20, 30, and instead of here on the slide it says 10, 10, 30. Yes. Great question, though. Absolutely. So, yes. Well, with that, I'll continue. We'll look, besides the things that I've shown so far, we also have a splitter. Of course, so if you have a composite or an atomic stream, you might want to split it. That's a quite useful operation. Because of time, I have to skip through here. What can I say about workflows? We've seen the workflows now. A workflow consumes an atomic stream and produces an atomic stream. That's the general, that's what it does. And the portals, here we can look a bit more in detail what portals are. Here I'm showing you, especially you should look at the code here. How does it work or how do we even define something like this? Well, to define a replying workflow, first you create a portal, which is, can I use this mouse? Yes. Yes, here you can see we define a portal up here. And then when we create our task, we say it's a replying task. We bind it to the portal, and you need to have two handlers here. One handler for handling just regular events that come in. These are the events from the source, and the other one for the requests. On the asking side, we have again we fetch a portal from some registry by the name, and then we create an asking task. We bind it to the portal, and what you can do here is you can ask this portal the request. I see you get back a future, and you can wait on this future, and you pass it a continuation, which then is executed when the future is completed. So this is the general workings of how we can use it. Yeah, a nice example showing how we can use it is in the cart of the shopping cart. So here we have again an asker task, an asking task that binds to a portal, and then it matches on the client's request here. If it's an add to cart item request, then we can ask the portal, which is now towards inventory, if we can get the item, and we can wait on the future, and so on. So pretty basic how you would expect it to work. Yes. What I want to talk about next is more fundamentally how the atomic processing works. That's what we call how the processing units process things. And in a logical sense, this is when I say logical, I mean how it is observed to happen. The workflow or any processing units, you take first does the following steps. It takes one atom from the head of the queue, then it processes it until it's fully complete, and then it commits to the output and repeats this. And again, this is in the logical sense how it executes. But of course, it would be it's not very optimal in terms of execution, as you could actually start processing the next atom before you're fully finished by using pipeline. So you can actually do this by the problem is if we start processing the second atom before the first one has finished fully, as on the left side of this slide, you can see that the yellow events might overtake the green events here. Because we have forks and joins in our task graph, this might happen. So instead, you can use an alignment protocol. It's in essence very similar to what is used by Apache Flink and the other systems, where you have broadcast markers, or we call them atom barrier markers. And what you have to do is the task has to processes an incoming edge. That's what you see on the top right of this slide, until one of these markers comes in at the edge. And then you start buffering on this edge. And you do this until all of the edges have now received the markers, at which point you can continue again. So, and in essence, this is also part of how we can do the exactly once processing mechanism. I promised something on event orderings earlier in the talk. One observation we can do is that the atoms, or one of the properties of the atomic stream, is that the atoms are in a total order. So we have some implications from this that, for example, if I have two events from two different atoms, they are also in an order, and they will be processed in this order. We can promise this. And we also have another implication, which is that these implicit atom barriers, which are these implicit events between two atoms, they're also in a total order to any other event in the stream. To make it a bit more concrete what this can be used for, well, one of the issues is normally that you might have some conflicts between events. For example, if I have one event that wants to erase, in a very real use case now, erase a user from a system. So imagine one of the users you have wants to be erased from your system. This is now a required operation according to GDPR. How do you ensure that this erasure happens and the user is fully erased? One of the problems is if you don't do this properly, you could have a read, some event that reads the user, then you apply the erasure, and then the first event writes back the user somehow. So this could happen if you have concurrent reads and writes, which we do have here. So one solution could simply be to have this erase operation to be the sole event within an atom. Of course, this would mean that this is the sole event to be executed on the workflow in the logical sense, with no other event being executed in the workflow. Of course, this might have quite a high overhead, so one could try to batch these events instead and execute them instead on this barrier that we have, the atom barriers. That's another option that we're exploring, as shown in the bottom figure. Yes, as I alluded also, the atomic processing is also part of what we use to enforce end-to-end exactly once processing RTs. If there are any questions, we can talk about that later. In the paper, what do we have more? We have a very nice section on exactly once processing, if that interests you. We also implemented a prototype in Scala free and have evaluated it. We talk more about use cases and also a lot more about related work. So I suggest everyone here to take a look if they're interested. For future work, we're working on implementing the distributed and decentralized version of this, hopefully done by next summer. And we have a very talented student also working on the formalization of portals. We're hoping to generate some nice proofs. And finally, we're looking at some interesting extensions. Most very important would be to split atoms, because one real issue would be that the atoms can grow very large, at which point you have issues because of that. If the computation takes too long, you might have it so that it's very likely that it crashes once you process a single atom. And some more extensions, perhaps actor-like references added to the system. Yes. And that concludes my talk.
Thank you, Dennis. And people have questions about this before we all fail for lunch in 2 minutes. Marco, question asker.
It seems like you are suggesting the portal to be used for this internal state, but it looks like it would be a very good interface for representing any kind of data input. Like observing the state of the result of an HTTP request could be masked as a portal, and there will be no difference for the user if this is data that is internal to the system or coming from outside. Is that already what you're doing? Is the extension? Is
what the it sounds like an interesting idea. Yeah. The main the reason, first of all, we started with this is that a lot of these actual companies that use Dataflow Streaming systems, for example, they might run a join on some users, and simply they cannot query the current state of the system, so they hack in the queries. And the issue with this is either it's you get inconsistent reads, which might be a read of something that might fail or has failed, or simply it's a very ugly solution where you kind of have to work around the system to do it. That's our main use case, I would say. But we're also looking to having a local version running where we could do things as you mentioned also. But I don't know if it applies as much to having it running distributed, what your example would. But we can talk later, perhaps.
I was curious about, you were talking about when you have a cycle, you have a sequencing operation for the atoms, for feedback edge and the forward edge. What you do have a rule on the ordering that gets imposed by this sequencing operator? How do you decide which atoms go first as opposed to once you're between the feedback edge and the forward edge?
Mm-hmm. Well, with the sequencer, the only we're considering still two options. Right now we have it so it's random. So it's really a random choice. The other option is to have potentially a strategy where you can choose. You can define a strategy in which order you might want to pull these items in at the sequencer, which I am not sure if it does make sense, because some strategies might actually have the effect that you have a deadlock. For example, if you're waiting for an input but it never arrives, then you would have a deadlock. So it's still an open question, I'll say. But
Any other questions? I'll ask one briefly. So systems like internal ones from Microsoft that sort of working on probably Pony and related stuff there offer causal ordering across actor systems. How is what you've done here related to that?
Yeah, so we don't have exactly causal ordering like that, but we do have some. If you have two events in two following atoms, there is an order between those two, right? So if I have one event in one atom, then in a subsequent atom, an event, there will be an order between these two. But the causal order does not span across many workflows, at least not currently. So if you have a larger deployment with many workflows and many atomic streams,
streams fed them into two things, then maybe you would lose that.
Yes. So exactly.
All right. Let's thank the speaker again. And,